Big Dig, kind of affectionately or not so affectionately known in Boston. It was the largest U.S. civic infrastructure project in the history of the United States. And if you look at the metrics there, they're just kind of, you know, like hard to fathom. 5 miles of tunnels, 200 bridges in a highly densely populated urban area. But the metric I'd like everybody to take particular note of is at the very bottom, that in addition to all these amazing things that needed to be done, the project was billions of dollars over cost in years behind schedule. And what you're going to see is that decisions were made that were very mindful of those schedule and cost pressures. So, whoops, you said it was temperamental. So the story begins, September 1999, a construction contractor employed, not an engineer, not a quality inspector. He noticed that some of the fasteners in the tunnel ceiling had started to pull out. And he said, or at least he thought, you know, whoa, this just doesn't look right. So he called in his boss, who called in his boss's boss, and they pulled in the engineers to evaluate what the deal was. So they performed proof testing on this particular fastener and a number of others that had also been observed to have pulled out. And the behavior was not what they had ever seen before, not what they expected, that it held fast, strong at the proof load pressure, but then it just slipped out very quickly. So that was a pointer to a causal factor that was not understood or seen at the time. So this is what the contractor employees saw. So they did what you would expect them to do. You know, the construction company and the engineers, they called in the experts, the fastener supplier who provided the fastening system. And they came in and looked at it and they scratched their heads and said, you know, I don't know. This was proof tested. It passed. It had to be you guys. You know, the concrete wasn't right. The cleaning procedures weren't adequate. The preload was excessive. Some other reason besides the fastening system being inadequate. Didn't do anything beyond that and then walked away. So you're left with the builder, design agent, project manager trying to figure out, okay, the experts have spoken, so they fall back to tried and true proof testing. And just to show you the seriousness that they took this for, they went at it with vim and vigor. The design service load was 2,600 pounds. They had been previously strength tested to 25% over the design load, 3,200 pounds successfully, all of them. And then to show the seriousness with which they took this defect, they went all the way up to failure, pre-failure, maximum allowable load, and tested every single fastener and felt that they had really done their due diligence. And to complement that, they performed finite element analysis just to verify their design assumptions concerning the design loads, and everything checked out. But this didn't sit well with a number of engineers. Later on, emails came out between the first is from a design manager, and then the reply is from a structural engineer. And he points out that the key piece of information missing is the cause of the anchor failure and how the repair procedure is going to fix that. And then the reply from the structural engineers basically agreed with this. It glaringly absent is any explanation as to why they failed and steps to show that the problem doesn't reoccur. And when I provide the same presentation to quality persons, I always have, where is the voice of quality? Why didn't they throw down that red flag? You know, causal factor was not identified. You can't, don't pass go till you figure that out. So not surprisingly, it happened again. So this time it was a quality inspector, and he noticed that fasteners were again slipping out, but these have been tested to 6,300 pounds, so the full maximum design load. Reason for failure unknown. And later on, after the accident, the NTSB came in and said, at this point, it really should have been obvious that they hadn't identified the cause, They hadn't implemented effective remedial measures, yet they kept treating it as isolated instances. And you know, as a long-time quality professional, I can't tell you how many replies, this is most early on in my career, came back, you write a quality deficiency, and it just is isolated incident, you know. Rarely is it an isolated incident. And then it happened. Okay, so they didn't treat it systemically, just a bunch of isolated cases. And this, it just kind of is mind-boggling to me that when the inspector noticed some that had slipped out, they didn't do 100% inspection. That would have been quick, easy, cheap to do that. So in any event, the accident occurred. 26 tons of concrete detached from the roof, landed on a passenger car, and killed the passenger. So the NTSB came in, did their accident investigation, and the proximate cause was determined to be the use of an epoxy anchor adhesive with poor creep resistance. Say what? It's like, for me, I read that and I thought, okay, what is creep? Does anybody here, for the entire hours, know what creep is who didn't learn what creep is by coming to understand this accident? Not me. Yeah, so, in fact, even the term sounds rather non-technical. So creep is a biochemical process. It occurs in polymers when the molecules are rearranged with time and pressure, time and force. And it was not at the time, an unknown phenomenon. It was documented in multiple technical standards, yet the persons on hand at the time did not know anything about this phenomenon. Pointed in the wrong direction. So I'm going to go over a few schematics, and each of these identifies what I call a contributing causal factor of a design vulnerability. The first of which is the ceiling was held in place by these rods and these fasteners, and it didn't need to be. Most tunnels constructed at that time had continuous ceilings. They didn't need to be suspended ceilings. Much safer design. Next, ceiling panels made of reinforced concrete slabs. Initially, the ceiling panels were lightweight laminate ceiling panels, and then a cost savings and engineering change proposal came in that, gee, it would be cost a fraction to just make these out of concrete. That was approved. A lot of money was saved. But as we see later on, the force and time factors combined resulted in the failure of the ceilings. Whoops. So, lastly, the design vulnerability. They used basically glued-in studs. Didn't need to do that. Mechanical fastening systems were recommended by engineers and discounted or discarded in favor of this, which had inherent vulnerabilities. And just point of note, the epoxy itself, not just the stud, is a safety critical item. Its failure can cause loss of life, and it did. You'd never expect that. So we're going to get into the unknown knowns. So, and this is so relevant to the discussion we just had. So corporately, the supplier manufacturer knew all about creep. In fact, they had tried to successfully pass these fasteners for creep, but the individuals that had been called onto the scene to investigate this had no knowledge of that. The knowledge had not been captured and transferred to the right people. And as the safety board says, you would have expected, at a minimum, the supplier of a safety critical component to be more proactive in determining why the fastener was failing. And not just the supplier. You know, culpability is kind of spread among multiple organizations here. Designers, contractors, managers, overseers, nobody had any knowledge of this phenomenon, even though it was being used for safety critical purposes. And this gets back to the initial slide, or one of the initial slides. even after being presented with evidence of anchorcrete, striking evidence, that they didn't recognize the weakness. And no matter what they did, all the best installation practices, all the proof testing in the world, it wouldn't have fixed this problem because it was the wrong solution. So now we get into why. How could they have missed it? And there are a couple terms I'm going to throw at you. The first is cognitive dissonance. It's a psychological term. Effectively, all of us do it. We have our own experience, our own knowledge, and everything we see, we filter through our knowledge and experience space. And if you see something that just doesn't align with that, it doesn't compute, it's beyond your reality, you filter it out and come up with explanations that do fit your knowledge and reality base. And that's what occurred. It's also referred to, or very similarly, as failure of imagination. And this term was used in Apollo 1. It's also been used for other major catastrophes, 9/11, Titanic, Pearl Harbor. And it's also called the black swan factor. It's when in hindsight, it's basically hindsight is 20/20. In hindsight, it was obvious it was going to happen. It had to happen. You just couldn't see it when in the present time. So this is a little kind of a footnote because I don't want it to be missed. And I'm not getting into all the causal factors. There's so many, but this one is particularly relevant to this audience. The question was asked yesterday about the adequacy of technical standards. Well, this is a case where the technical standard fell flat. It gave an option of either performing a creep test or a design safety factors, effectively a proof test of 5.33 times the safety margin. And the NTSB found fault with that for good reason. It's like, as you've just seen, proof testing did not prove the safety when you have epoxies involved. So the supplier, not surprisingly, to support product qualification, they provided an engineering report that showed that they satisfied the safety factor of 5.33. It later came out in the accident investigation that they had tried multiple times for their fast set epoxy to pass creep testing, and it did not. So here's a case where they provided something that they had corporate knowledge of was not adequate for that application. And this is what it looked like after the accident investigation. Anybody, your child, your grandmother, your dog, if it's a smart dog, could have seen that and said, this is not right, yet that nothing was done to make sure that they had remedied this problem through their proof load testing. And the last slide I have here is just kind of an add-on. I came across this last week and I mentioned it yesterday. How relevant is this to NASA? In a very general sense, yeah, lessons learned that have broad application, but even more specifically, how relevant are the behaviors of carbon fiber polymers? Well, they might be extremely relevant, so it's good for us to learn and heed lessons from other arenas. Destination Disaster is the name of a book written by Paul Eddy, terrific book that chronicles the events leading to the loss of the McDonnell Douglas DC-10. In March 1974, left Paris, and at 11,500 feet, the rear cargo door blew open, creating an explosive decompression, and the bomb lost all its control surfaces and crashed in a floor in France, with all persons lost. Proximate cause determined to be a faulty latch. Again, it's like one sentence summarizes it, just proximate cause. It's so simple. An epoxy adhesive, a faulty latch, yet there are multiple causal factors that are all interrelating, but often the proximate event is something very, very simple in its nature. So a bit about the latches. The schematic on the right has a latch properly closed. On the left has a latch that is not properly closed. So if you look at my hands here, so you have this restraining plate, and you have the lock pin. So when the door is shut, the lock pin slides into place, and the restraining plate can't move. The door is secure. When the door is open and the lock pin hits it, you can't you physically can't latch it. At least you're supposed to not be able to latch it. What actually occurred is that the lock pin was bumping up against the retaining plate, but if you push down hard enough onto the door latch, you could actually close it, or think you had closed it. Multiple complex linkages, and to quote this, a baggage handler of normal strength could push the handle fully down, thinking he had thus secured the closing door, when all he'd done was bend the internal bars and rods out of shape. Whoops. So this, the book again is rich with insights and wonderful quotes. So this is his comment upon the integrity, the goodness of the latch design. And this is a great segue. Because they had such a poor latch design, the other safety factors became critical. And this is where we get into design vulnerabilities. He says, because you had a gimcrack, I've never heard that word before, I like that, latch design, safety in every man, woman, and child aboard the DC-10 was dependent upon the efficacy of the linkages from the moment the plane went into service. So what are the contributing causal factors from a design perspective? The door configuration, it was an outward opening hatch door. Not a bad design choice. If you recall, the Apollo 1 had a plug design, much safer from this perspective, but outward opening doors left more room inside the airplane, which meant more passengers, which meant more revenue. So economically, it was a better choice for McDonnell Douglas. Not a bad decision, but when you made that decision, similar to the Apollo 1 decision to have a plug design, you need to mitigate that with appropriate design choices. And some of the design choices, routing of cables, hydraulic lines, and wire, they were in the floor, immediately above the cargo department. And when the explosive decompression occurred, all those were lost. Floor strength. Again, design choice to have a floor that could not withstand an explosive decompression, even though the possibility existed. We've talked about latch design, cockpit indicator and vent door design. With the cockpit indicator light on, because the door had not been shut, the pilot would not be permitted to take off. If the vent door was open, then it would be impossible to pressurize the cabin. The plane could not take off. But both of those were operated from the latch itself. So if the latch is down, if the handle is down, the light went off, the vent door was shut. Bad, lack of safety design principles. And now we're going to get into what you might call unethical behavior. Convair, a subcontractor to McDonnell Douglas, performed an FMEA, and it showed definitively that the deadly consequence of a cargo door latch failure, but the FMEA never made it to the FAA. So that was a decision made on the part of McDonnell Douglas, the first of many bad decisions. So the gift occurred. So here we have no loss of life, no loss of significant property. This was just a simple air conditioning system test that they took the compartment to 4 to 5 pounds of pressure, which is roughly equivalent when you're at 11,500 feet. It's amazingly how consistent that is. Lower cargo door blew open, large section of the cabin door collapsed. So not only did the door blow open, but the floor collapsed with all the control surfaces. And McDonnell Douglas attributed the incident almost entirely to human failure. So, how convenient, how expedient. They didn't really need to pursue it any further. Somebody just screwed up. This didn't sit well. Again, similar to the last example, with an engineer at Convair. He wrote a memorandum, which actually is used, I've never seen it used in this capacity, but used in engineering ethics course. It's called the Applegate Memorandum. And he basically said that it would, based on the latch design and what happened with the air conditioning decompression incident we just talked about, he said, it seems inevitable that in 20 years ahead, of us, the DC-10 cargo doors will come open and cargo compartments will experience decompression, and I would expect this to usually result in loss of the airplane. And he was exactly right. And as proof of that, we'll call this another gift. This actually occurred in flight. American Airlines flight left Detroit, got to almost the same altitude. And I'm actually, as a quality engineer, I'm kind of impressed with the variation management, the process controls. They had a very tight bell curve. These failed at exactly the same place. Of course, you know, the bell curve was yards to the right of where it needed to be, but it was tight. They always failed at the same time. But the crew, you know, heroic aspects managed to get the plane back to Detroit. And the NTSB came in, as they had to, and hit the nail right on the head. Design characteristics of the latch mechanisms permitted the door to be apparently closed when, in fact, they were not fully engaged and the lock pins were not in place. The truth was out. McDonnell Douglas couldn't say otherwise. And from this, it really gets almost into the realm of disbelief. So the NTSB provided a report. They provided recommendations to the FAA, and the FAA proceeded to write an airworthiness directive, and they had it almost ready to go when the president of McDonnell Douglas called the FAA administrator and persuaded him that he really didn't need to write an airworthiness directive, which, for those of you who know, that would effectively ground the DC-10 fleet. It would be against the law to fly until all the remedial measures had been put in place. So the FAA administrator capitulated, agreed to other measures. Whoops. I'm not going to comment on this. I think this is a great quote. Thousands of years old, but it's just so spot on. Okay, so these are the measures in the NTSB report that were agreed to by McDonnell Douglas. Install peephole with the decal showing what it's supposed to look like when the locking pin is securely in place. And install a support plate to hold up the torque tube just inside the handle. You probably don't recall, I should have pointed it out. In the initial diagram of the latching mechanism, on the right side, there was a little piece of metal directly below the torque tube so that it couldn't bend. So if that, in fact, had been done, the door, you couldn't have shut the door and the accident would not have occurred. But, there's always a but. Whoops. Come on. So, first of all, a kind of a maintenance card that was agreed to. Hundreds of these are issued every month. And when the accident occurred and they looked at the inspection records to show that the support plate had been installed, showed clearly 3 inspection stamps. Yep, they verified with certainty that they'd been installed, but the 3 men were brought forward, examined under oath, and none of them could recall ever having worked on that door. And to make matters almost comical, one of them was an electrical inspector, would have never have been inspecting a mechanical component like that. But Douglas didn't back off. To the end, they called it human error and the falsity of the records. And that company, as you know, is no longer in existence. Another good quote from Pauletti. So I can tell a story then, a little bit of a story. So I reported to Newport News Shipbuilding 35 years ago, young, impressionable, eager quality engineer, and here's your cubicle, here are a couple of things we want you to read, and then come talk to us tomorrow. So one of those things was the congressional proceedings for the loss of the USS Thresher. And I dutifully read through that, and as I read through that, I was just so astounded. I had never known anything like that could exist. The series of events, each of which individually seemed unlikely, but the compounding of them, or their overlapping at a point in time to create the loss just seems remarkably unlikely, remarkably unfair. I later learned, after studying other disasters, that it's really not so uncommon. It's for for most mishaps where you have highly complex systems interrelating with each other, there are multiple causal factors that have to all align. So I'm not going to talk about the Apollo 1 because it was talked about yesterday, and most of you know the details of that. The only things I'll point out here is both the Thresher and Apollo 1 were brand new platforms, first in their class, and with brand new stuff, obviously technical innovations and advancements are essential. Vitally important are good things, but they come with risk. When something is new, your safety senses ought to be tingling. It's unproven. And it's impossible to prove something that's new. You can do as many analyses, engineering, but empirical evidence, demonstrated reliability, there's no substitute for that. So both of these, first in their class, leading edge of technology at the time. Loss of the Thresher, like the Apollo 1, it was lost in a testing evolution. All men aboard perished. Whoops, keep doing that. So here's what happened with the Thresher. Somebody got up in the morning, had their coffee, went to work, and did a bad job, a sloppy job, brazing up a pipe joint. And it was the wrong pipe joint because this one was exposed to full submergence pressure. And when a submarine is hundreds of feet deep, and the seawater systems, internal submarine, are exposed to full submergence pressure, tremendous pressure. And so the first point here is that it should never have been a brazed joint to begin with. Welding joints were known to be stronger and more reliable, yet this is a very bad design decision. So this guy, whoever, probably a guy at the time, performed a bad joint, and it failed. Seawater sprayed from the joint onto a control panel, and that control panel shorted out, causing the reactor on the Thresher to scram. And submarines, it's not like the movies where, blow, blow, and submarines bobs to the surface. Submarines operate under essentially neutral buoyancy, and they drive up and down by propulsion power. So they had no propulsion power, so they had to blow the ballast tanks. And when they did that, turns out that the very well-known physical principle at the time, expanding gases, cool, basically, decrease in temperature. I can't remember the name of it. It's Joule something principle or something like that. It's what makes your air conditioner and your refrigerator work. So there was water in the gas, and the water turned to ice, and it plugged up the high pressure air piping, so they weren't able to blow the ballast tanks at a sufficient rate. And so the evidence is that the Thresher started to surface, and then it sank because seawater was gushing into the submarine. And so we get into another design vulnerability. It's called access to vital equipment. The seawater valves, you need to get to them very quickly when you have an incident like that and shut them. So seawater is not continuing to get into the submarine. And apparently that did not occur on the Thresher. So, the story just goes from kind of sad to sadder. So it's hard to believe for NDE professionals that UT could ever have been a new technology, but it was a new technology in the early 60s, and they were using it on the Thresher. And what they found is that a surprisingly large percentage of brazed joints didn't have sufficient bond. So what do you do in the quality world? You develop a sampling plan. First of all, safety critical should not even have been a sampling plan. It should have been 100% inspection, but they didn't do that. So they inspected it, and if you do sample it, and you have you should have acceptable reject rate is 0, which means if you find something, you stop, you inspect 100%. And they found a lot of rejects. It means they didn't stop and inspect 100%. So basically, the quality community fell flat in this case. And then I think I've talked about all this. So you have quality shortcomings, manufacturing shortcomings, design shortcomings that all came together at the same time. And I'm sure you've all seen this before. I do want to back up if you've never read this from Fallen Astronauts, it's pretty moving, frankly. It says, reasoning behind the use of pure oxygen seems sound enough. If you go to the last sentence, proved to be a fatal error of reasoning that easily contained fire in space at less than 6 psi would become an explosive inferno. At 16 psi, it's failure of imagination. Didn't even imagine this particular scenario. Okay, I'm going to jump into a couple things very, very briefly. Fraud. This would not have been on my matrix of common threads if I had done this 5 years ago. Fraud is a very real and present danger. NASA has lost tremendous assets. Others within the Missile Defense Agency, and I'll get to it, even our Russian colleagues. So we need to be mindful of that. We need to use different tools from our toolbox to combat it. So about a year ago, an advisory was written that said that SAPR profiles, and I'd never even heard of SAP before, they happen to be the largest producer of aluminum extrusions in the world, may have altered mechanical property test results performed on aluminum extrusions. When you see may, take your pencil and cross that. It means an attorney got their hold of it and provided their input. In fact, the company itself, confessed very quickly that, yeah, this had occurred. So why the big deal? Well, these aluminum extrusions were used on the frangible joint hardware for the Oko and Glory satellites. And one of the primary causal factors for the loss of those two satellites was the aluminum extrusions with inadequate mechanical properties. So way big deal. Didn't see the fraud coming and didn't have proper mitigation measures in place. And I will say, related back to the comment on engineering standards, there is a highly used quality standard. Tens of thousands of aerospace contractors and subcontractors use it. It's called AS 900. In the Rev B edition, there was a requirement to validate the accuracy of test reports. To NASA's strong objections, it was taken out. Rev C became in place, didn't even have that requirement. That was in effect when this incident occurred. And then Rev D, which just came out a couple months ago, again, to NASA's victory in NASA's part, because of all the incidents, we put together pretty convincing reasoning as to why this needed to be back in AS 900. It's now back in AS 900. So all of our contractors need to verify in some periodic significant way the accuracy of test reports. Just don't trust it. It may not accurately reflect the materials provided. Counterfeit parts. So a lot of times people think, oh, somebody else's problem, somebody else. It's not somebody else's problem. NASA has procured numerous counterfeit parts. Our prime contractors, dozens more. And the Russians, the most plausible causal factor of many postulated causal factors for the loss of the Phobos grunt probe, highly visible, highly costly probe that was going to go to the moon of Mars and collect samples, bring them back to Earth, was lost. And the most likely causal factor, primary causal factor, was they bought their electronic parts from foreign sources because they were a whole lot cheaper. And wow, I mean, the warning bells would hopefully just go off like crazy here if NASA did something like that. Whoops. Okay, let's try again. So those are not isolated cases. The drumbeat just goes on over history. It's always been an issue, percolating along in the background. It doesn't really get our attention. 10 years ago, M&M Metals, a Honeywell inspector, looked at a bunch of test reports and noticed something kind of funny, that the mechanical properties listed for various heats were exactly the same to the third decimal point. It's like, gosh, that doesn't smell right. So he contacted others, and turned out there had been gross fraud, falsification of records. Western Titanium, roughly 5 years ago, had been basically slicing billets. They didn't cold work, roll, forge, heat treat the billet into the final aerospace grade metals. They just sliced it, and it looked, smelled, felt, came across as finished aerospace grade. It wasn't. And so NASA bought tremendous quantities, as did DoD. A&P alloys. One of the interesting things that came out with Western Titanium was that another metal that had the same economic incentive to titanium was steel. So Lockheed Martin found that the same exact case with A&P alloys. And then just a couple last slides. This is different than the other incidents. This is the more recent, and we're really getting up almost into present day here. So this is a case where a machining error had been observed in a previous acceptance test, and it was known, and it was an accepted risk. So the point here is that it's really the gravity. It's not to second guess the decision made, but to just point out that the gravity, the importance of the decisions, the rigor that must go into decisions when you're accepting risk. Whoops, gosh, I keep doing that. Okay, proceeding further into modern day, just last year, the rod end of the strut was 5 times less the mechanical properties called out on the design specifications. Single item caused loss of that launch platform. And this, I found this quote from Elon Musk to be, whoops, gosh, my apologies. Refreshingly open and honest. He blamed overconfidence. When you only ever seen success, you don't fear failure quite as much. But when I read that, it brought me back to a presentation that the chief engineer at ATK provided about, I don't know, several years earlier at a quality leadership forum. And he was describing the characteristics of high-performing organizations. One of them was a preoccupation with the prospect of failure. And then that, again, triggered a memory of a quote from our own Gerst. What we really learned from the Apollo fire was a failure of imagination. And the message to our team, and this is my concluding message, remember how difficult our business is and the importance of staying focused and using our imaginations to envision what can go wrong. That's all I had. Thanks.